Chapter 26, warm up in super speed, because I just recorded it a minute ago and deleted that recording. So I'm going to speed through this. All right, this problem is a chi-squared goodness of fit because it is only about one group. If it had been about more groups than just the biology, then it might be something like a chi-squared test of independence. For example, if this had asked about biology, English, and math, then we would have a department variable in addition to the grade variable. That would make it a chi-squared test instead of chi-squared goodness of fit test. It being a chi-squared goodness of fit test, we're going to go ahead and put the information in the list. Here's how you do that. You need to put the observed values right here, the observed values, into list 1. You need to put the expected values into list 2. The expected values come from the percentage that they told you to expect times the total observances. So in this case, 15% of the total 325 should be A's, so therefore that's 48.75. That doesn't have to be a whole number because this is what you would expect on average in the long run over many samples over the course of time. All right, the null hypothesis, the professor's most recent grade distribution matches what's historically distributed, and the alternative, it does not match. Your conditions are only over one group for these problems. The one group of the professor's students. Random, assume these are representative. Independent, 325 is less than 10% of all this professor's students. And large enough. You can see from the expected counts that the expected counts are greater than 5, and they are all listed here. You must list them so that you can show them and quote-unquote prove that they are all greater than 5. Do not forget to conclude with chi-squared model applies. This is a chi-squared goodness of fit because we're seeing how good the data you have fits what is expected to happen. Running the test gives you this. Please notice that the p-value is not 8.49. It's 8.49 times 10 to the negative 13th, which is about 0. Your degrees of freedom are categories minus 1. That's 4. So with a p-value this low, we reject the null hypothesis. So I reject the professor's most recent grade distribution matches the historical distribution. I have evidence that he is or she is issuing grades at a different rate than previously. Which grade impacted your decision most? Explain what this means in context of this problem. You need to determine how this relates to what was expected. So for each one of these grades, we're going to do a standardized residual. A standardized residual, as you can see on the formula chart, this is the back of your formula chart. If you look down here at the bottom, you can see that the observed minus expected quantity squared divided by expected is the component for individual ones. They would always be a positive value because of the squaring. And so that when you added them up, when you summed them up, you get a proper chi-squared value. Now, the downside to using this formula up here is they are always positive. So if you want to see how values compare to what's expected, then that doesn't help you in the direction sense. So in order to do a standardized residual, you need this formula, but in its unsquared form. So that observed minus expected is not squared. And the expected is actually the square root of expected. So this is the formula that you should use for each place for the standardized residual. So if we look back to this, I want to show you how to do this in your calculator. I have the observed values into list 1. I have the expected values into list 2. So in list 3, I am going to formulate what you see here. And in list 3, I'm going to put the observed minus expected and put parentheses around that so that when I put divided by, it's dividing the whole sum or the whole difference. Square root of list 2, which is the square root of expected, so here it goes. Parentheses, list 1 minus list 2, close it up, divided by the square root of list 2. So that gives you then, I have to go to, I've made an error. So I did not put my cursor on top of the L3. So let's make sure your cursor's on top of L3. Parentheses, list 1 minus list 2. Close the parentheses, divided by the square root of list 2. There are now these expected values. And you can see, as asked, which grade impacted your decision most? The grade that impacted my decision most was the A's, because that was farthest away from expected. Furthermore, notice that the professor gave A's and B's more than expected, and the professor gave C, D's, and F's less than expected. These residuals are related to the expected value. Okay. Next, on this side, we've got two variables, gender and breakfast. Okay? Now, I would go with using males and females as my two groups that I'm going to do conditions on. Okay? So we'll end up putting that into our matrix, and we will end up doing conditions for two groups, the male group and the female group. Because this asks if there is evidence that eating breakfast is independent of the student's gender, then this is a chi-squared test of independence. All right, let's talk about the null hypothesis. Is eating breakfast is independent of gender. Alternative, eating breakfast is not independent of gender. Conditions is for males and females. Assume males and females are representative of all males and females. Independent, 133 males is less than 10% of all males. 199 females is less than 10% of all females. The groups are independent of each other. Large enough, as you can see from the expected table above, that all expected counts are greater than 5, and you must give and show this data. So let me talk to you about that. I want you to be able to do that by hand and with your calculator. To get a location for a cell, you need to do the row total times the column total divided by the total. And that is how you can, by hand, compute each one of these. So for this 76.17, that came from 132, the row total, times 191, the column total, divided by 331, the total. And that's how I got 76.17. All right. Do not forget to conclude your conditions with chi-squared model applies. Chi-squared model applies. Now, I want to run this chi-squared test of independence and explain to you another way that you can get all of these expected values. So if you go to second x to the negative 1, and you go into matrix A, I'm going to go into edit matrix A. It doesn't matter what you have in matrix B. Running the test will paste over anything you have in matrix B. So you don't have to worry about deleting stuff in matrix B. So I'm going to go into matrix A, and I'm going to put in my 2 by 2 data, 66, 125, and 74. When I then go stat over to test and run a chi-squared test, then it says I put my observed in A. It will create the expected matrix in B. So then we go down here and we calculate, and voila, there are the chi-squared value, the p-value, and the degrees of freedom. So I have written those down here. Okay. Now, furthermore, let's talk about a good way to view this expected matrix here in your calculator. The best way to view it is to go to second x to the negative 1, and the best viewing is done in the edit mode. So go over to edit, down to B, hit enter, and then voila, there are all of those expected values. And I rounded accordingly to the decimals. Okay, so that is the way to view your expected matrix B. View matrix B to get this expected in your calculator. All right. So since our p-value is less than alpha, we reject that eating breakfast is independent of gender. It seems as though there is some kind of correlation between gender and eating breakfast. Although this did not ask you, I went ahead just for practice, do these standardized residuals, and you can see that for each one of these spots, I did observed minus expected over square root of expected. So what you can see is that males eat breakfast less than expected. Females eat breakfast more than expected. And if you were to talk about the value that contributed most to this chi-squared value, you would say males not eating breakfast, males that do not eat breakfast, that group contributed most to this chi-squared value because it is farthest away from expected. All right, there was a quick review of the chi-squared test of homogeneity and the chi-squared goodness of fit. Sorry I went so fast on that, but you can watch it as many times as you need and slow it down and stop it and all that kind of good stuff.